Welcome, everyone. I'm grateful to have the opportunity to present here, and I want to talk about telecentric optical systems for end-of-line inspection in electronics manufacturing. My name is Andreas Wegner-Berndt. I'm Managing Director at Vision on Control and responsible for the value stream and for administration. Looking at the abstract of my presentation, it is that more and more companies see the establishment of high automated manufacturing processes as an opportunity to increase the customer's value of their products. And automated mass production of high quality products is a key leverage to keep the cost targets also in high wage countries like Germany. Optical end-of-line inspection is getting more and more important, and telecentric imaging takes a key role when it comes to precise measurements and perspectives. Electronic manufacturing is far ahead of other industries, but there is room for improvement and advanced development. And let's talk about this. But first of all, I want to express Vision on Control's mission. The why of our company, it's to make machine seeing to support our customers' exceptional performance level. Vision Control was founded in 1991, so it's looking back on a 32-year history. Our campus is located in Suhl. It's exactly in the middle of Germany. It's called in the green heart of Germany, and we're a team of committed and experienced people who are enthusiastic for optics. And based on our in-house R&D and in-house production, we offer customer value made in Germany. Vision Control is a specialist for imaging components, which are strong in detail and even more in combination. We see three segments. That's optics, focused on telecentricity, lighting, matching to the imaging task, and industrial multi-camera systems. With our constantly growing catalog, we are in a perfect position to customize optical systems very fast. Looking at the requirements of optical inspection in electronics manufacturing, I will focus here on the inspection of printed circuit board assemblies, that mean PCBAs. There may be different requirements when it comes to solder paste inspection or semiconductors inspection. The optical inspection of PCBAs requires special know-how in terms of perspective and also image performance. In detail is that high precision of dimensions at any height level, so there are different height levels on the PCBAs, no concealed areas, minimized parallax errors, precise recording of component labeling, also on uneven or rounded surfaces, high precision measuring functions down to the micron range, quality grading of soldering junctions, and at last, the large area inspections of complete PCBAs or wide fields of devices. What does that mean, telecentricity? Using endocentric lenses, we see it on the right picture, the focal point is in the front lens. The objects on the image looking different due to the distance to the lens. Coming to the principle of telecentric imaging, we see it on the left side. By placing the aperture diaphragm, you see it here, in the focal point of the front optics, the main beam is forced to be a focal beam on the image side, and the main beam on the object side is running parallel. That's why objects of the same size are imaged in the same size, even at different distances. that results that also that we have no unwanted edge concealments. The principle shown in the previous slide was the principle of the object-sided telecentricity we see here on the left side. We see the aperture diaphragm is placed in the focal point of the front lens. We see the image side focal beam, and we see that the main beam and object side is running parallel. I'd like to explain also another type, the bilateral telecentricity. There is the focal point of the image side on the first lens section, and the focal point of the object side must meet the second lens section. The magnification is defined by the focal length ratio, and the result in a better compensation of optical aberrations. Telecentric lighting, coming to telecentric lighting, provides the aperture of the telecentric lens. That means that lens and light aperture can be perfectly aligned by the aperture diaphragm. The picture shows the principle of telecentric transmitted lighting. The lighting is opposite to the lens and the object between. The most common for PCB inspection is the reflected light principle. That means that light source and lens are on the same side of the object. Looking at some examples and application of telecentric optics for PCBA inspection. Looking on the left side and using an endocentric image, the components at the base of the capacitors, you see it in that red marked areas here, are concealed and cannot be tested. And on the right-hand side is the same part of a PCBA with telecentric optics. All electronic components on the PCBA are visible and can be tested. We see it in the red marked areas as well. Left side, you don't see these small capacitors, and on the right picture you see it perfect. And looking at these two pictures, using light in the red spectrum, the aperture must be much more opened and the depth of field decreases. And in contrast to this, using blue lighting, the lens can be faded down without blurring. The depth of field is much higher. I hope we see the difference on your screens. Under the name Blue Vision and Control have developed lenses where the color correction is extended into the deep blue spectrum, and combined with blue Vicolux lighting, we achieve that half wavelength results in double resolution and double depth of field. Looking at the US Air Force targets, in these two pictures, we can see that based on the identical optical setup, the blue light image looks perfect and sharp, and the red light image is looking much more blurring. At this point, I want to refer on my colleagues, Dr. Claudia Link's presentation at this platform, showing the physical principles very detailed, from macro to micro. Want to start with macro. A typical measuring lens for for that application is the Wycotar 88 series. For example, for this example, we used a lens system with a object field of 88 millimeters, an image field of 28.4 millimeters, which results in a magnification of 0.322, working distance of 130 millimeters, a variable aperture diaphragm, and a spectral range from 400 to 950 nanometer, which means that it is including the near-infrared spectrum as well. The pictures show the blue and the near-infrared image with the aperture f10. That means the diaphragm is open. You see, and and fading down the aperture to f16, we see a perfect depth of field looking at the capacitors on the right side and the surface of the PCB perfectly. So as you know, the capacitors are much higher than the surface of the PCB. Coming to micro, also typical is the application of microscope lenses for inspection of very small details. For this application, we used for this example we used a lens from our TOM series with an object field of 4.5 millimeters and an image field of 43.4 millimeters, which is a magnification of 9.644, working distance of 48 millimeters, the aperture f24, and also a spectral range from 400 to 950 nanometers. On the pictures, you can see the quality of the images at 470 nanometers, and looking on the US Air Force target, we see a resolution down to section 9, and we know 9-3 means 1.55 micron. Looking back to the requirements, we have seen that solder junctions have to be graded, and using telecentric optics, soldering junction often look dark or appear dark and can be graded properly. And the application of lens-mounted beam splitters for coaxial mirrored lighting allows the inspection of the soldering junctions very good. Here we applied the TO88 from the previous slides as a system with a beam splitter and lighting. Another more sophisticated solution for this requirement is lens integrated axial or coaxial mirrored lighting. Looking at this illustration, we see the principle of this approach. We see the classical approach, the coaxial lighting, and the axial camera with the beam splitter is integrated, and we have the axial lighting, and the camera is coaxial mounted. And our experiences have shown that the axial lighting version, this one, can minimize aberration effects like astigmatism if you manage the reflecting light inside the lens system. A further required use case is the assembly inspection of complete PCBAs or wide areas of devices, which require much higher lens diameters. and we know that exceeding a front lens diameter of more than 200 millimeter, the classical glass approach have a limited industrial usability because of the cost, weight, and mounting efforts. They are decreasing dramatically, and applying Fresnel lens designs for the front lens group, we see here, allows to realize lightweight designs for electronic inspection of large objects, lightweight compared to the glass alternative. And the biggest wide field lens that Vision Control physically realized was 59 by 58 centimeters. So it was rectangular. And looking on the principle of Fresnel lenses in general, we see it on the picture on the right side here. We see that the projected lens radius is segmented and applied on the flat surface. Fresnel lenses are molded parts and are made of high optical grade plastics. Coming to the customizing, and as we have seen, very versatile requirements have to be considered for inspection of electronic devices, and to get the best possible result, situation-specific optical systems get more and more important to reach the performance target. Based on our wide catalog portfolio, the path to a tailored lens and lighting system is quite short. Our team of innovative and experienced engineers will find the best solutions. Finally, I want to show a typical layout for 3D and 2D automatic optical inspection systems, which were kindly provided by Göbel Electronic in Jena. We see on the left side the typical two-dimensional layout, and we see on the right side the typical 3D and 2D combined layout, which are applied, for example, in a device like this you see here on that picture. Before I close, I want to express my thanks to Jens Kokot, product manager for inspection solutions at Göbel Electronics in Jena, for his support in validating the optical requirements of inspection systems. And I hope I did manage to spark your interest, and I'm open to your questions.